On Tuesday, welcome once again. On Tuesday, we started discussion on understanding statistics beyond the basic concepts. And we talked extensively about the fundamental concepts and how you can move your understanding gradually from understanding the basic concept to more advanced concepts. And I say that just like any endeavor in life, there is surely a starting point, and there's a link between the high and the low. So, and I keep on emphasizing the basic principle of leverage stats or leverage statistics, and the cardinal principles are presenting statistics to people without budging them down in equation or formula, then trying to move from very basic to advanced concept in a gradual manner, then facilitate use of statistical packages. So use innovative approach to enhance your understanding of usage of statistical packages. And those are the basic principle. And I said for some times now we started with the basic principle, we move gradually, some people have been following and they have benefited a lot. But some people lost track along the way and they just believe that something that is very simple, even chi-square, t-test, not to talk about ANOVA or regression or Poisson regression, they feel that it's too advanced for them and they don't want to leave the basic principle like a variable type of variable and mean standard deviation. So the aim of the lecture, as I said the first day, was to bridge that gap to let you know that there are some important aspects of the basic principle that will open your eyes to advanced statistics. So we made mention of the measure of central tendency and dispersion. Mean, we talk about standard deviation, we talk about variance. I also said probability is very, very important. It's key, very key to understanding statistics. And by next week, we'll talk much. We have discussed probability and normal distribution before, but we will discuss a lot of different probability distribution and how they are applicable in statistics. But I promise that today we look deep into how mean, deviation, variance, and standard deviation contribute to understanding advanced statistics. And I want to start with how you compute mean, variance, and standard deviation. So some people, it's very simple, but you may not know how it links with you understanding advanced statistics. So some people, it may not be simple. And if you cannot understand simple things like this, there's no way they can understand, that person can understand advanced. I don't want to say complex. There's nothing complex, just advanced. There's no nothing like complex statistics. It's advanced statistics. It's basic and advanced. Now, you usually use very simple approach, a simple example. We have an example here. The sample size here is 5. That is, we have 5 family. These 5 family, this is number 1, 2, 3, 4, 5. The subject, just the numbering, just to identify number 1, number 2, number 3. And the variable of interest is the number of children in the family. And if this family maybe went for a picnic, they are family friends, 5 family. And these are the number of children in each family. So if you are to the X now, the variable of interest is the number of children. And if you are to calculate the average number of children, all you need to do is that is the mean number of children, you add all of them together and everything is 25. So addition of X, which is sigma. Sigma is the notation. So we have some notations of what we use to signify addition. So sigma X means addition of all these X. 3 plus 4 plus 5 plus 6 plus 7 make it 25. Now, that is the average number of children. But we know that each family has number of children that differ from the average. So we may have one that maybe some that may have the same thing as average, but all of them cannot be average. So how do you know the number of the mean now is a measure of central tendency? We try to summarize, just give something that should be in the middle. So we expect that whatever is the mean will be the middle, it will not be too high, not be too low. So it's the middle number that will represent all of them. So when you see mean, you know that there are some that will be less than the mean, there are some that will be higher than the mean. Then now, how higher or how on average, averagely, what is the distance between each value and the mean, the measure of central tendency? And I don't want to jump and say, okay, the measure of central tendency is the mean, then the how far away each value is from the mean will be the measure of dispersion of variability. But I don't want to, we have discussed yesterday that there we have the range, the highest minus the lowest, like in this case now 7 minus 3, 4, the range is 4. Then we have standard deviation and variance. So how to come about the standard deviation and the variance is what I want to discuss here. And it's very, the understanding. It's not just to say, okay, measure of dispersion is the standard deviation. No. The logic behind arriving at that standard deviation. If you understand the logic, you will know how you will move to advanced statistics. You'll be able to understand how regression work, ANOVA, t-test, all those advanced statistics, if you can understand that logic. Now, if you look at it, now the intelligent people, how they thought then is human being like us, like you that advanced, that develop statistics. When they say, okay, how do we, because the reason for going for measure of dispersion, in addition to the measure of central tendency, it is because you know that this measure of central tendency, when you are dealing with quantitative variable, is not enough to describe the data set, because two groups of data set can have the same measure of central tendency, but the distribution differ. I usually say, okay, if you have a clinic, your clinic, you see the average systolic blood pressure of your client is 110 milligram per mercury, and milligram of mercury rather. Now, if another person has another clinic and the average also is 110 millimeter of mercury, will you say that both clinic, you have the distribution of the blood pressure of the people attend those both clinics are the same? No, you may not be able to say that, because for one clinic, the mean may be 110, but the value may be far apart. Maybe some will have even 80, 90, some will have 120, 200. So you see that a lot of the variability. Some may have extreme value, low, extremely high, even though the average is 110. And the other clinic, which the average is 110 also, the value may be close to that 110, maybe 120, 109, 113, you know. The values are around that value. That shows that for that second clinic, the variability is not much, even though the mean. So the variation around the mean, they are all close to the mean. While the other one, they are many, averagely, they are far, many are far from the mean. So because of that, using the mean alone or measure of central tendency will not completely describe the data set. So that's why intelligent people know, okay, why can't we know? How do we measure these, the average distance each value is from the mean? So let's go on. The first thing that will come to the mind, okay, why can't we remove the mean from each value? That is what we call deviation from the mean. Deviation. If you remove the mean from the value, some value that are less than the mean will give you negative value, because if the mean is bigger than those values, When you remove the mean, it will give you negative value. Those values that are the same thing as the mean will give you 0. And the value that are higher than the mean, when you remove the mean, it gives you positive value. That's what we have here. You just use this simple example because it's manageable. So it's the same principle that even with a big data set, the same principle. So when you look x minus x bar mean, x minus the mean x. So if you remove the mean 5, okay, I didn't talk about that. When we divide when you add all of them together 25, when you divide by 5, which is the number of the family, it gives you 5. The average is 5. Now, when you remove the average 5 from this, it gives you minus 2. You remove from this, it gives you minus 1. You remove from this, it's the same value, it gives you 0. And when you remove from it, it gives you 1 and 2. If you try to add the deviation together, it will give you 0. That is the same thing in all data set, because the mean is a middle value. So as many that are less than the mean are also more than the greater than the mean value. So that shows that if you remove the mean, as many that give you negative value, the same thing that will give you positive value. So when you add together with some that will be 0, it will give you 0. So addition of the deviation from the mean is usually 0. If you do it even in the large data set, you try to check it and it doesn't give you 0, it's because of approximation. The data you lost to approximation, it will be 0. Now, the intelligent people that say, what shall we do? Since we cannot go further, but we cannot add the deviation. So the mathematical rule, they understood that. Okay, say, why can't we square the deviation? Knowing that when you square the deviation, the negative value vanishes, because minus 2 multiplied by minus 2, that is minus 2 squared, will give you positive result. So when you square the negative, give you positive. So when you now say square deviation, you square the deviation, it will give you positive value. Now, if you call that one square deviation from the mean, x minus s bar square. For the whole of the data set, if you now, each participant will have his own, each value will have its own x minus s bar square. If you try to add it together, that would be the sigma, the addition of x minus s bar square. This is what we call sum of square. Because we're going to see it when we get to, when you run ANOVA, you run regression, you see sum of square. It's the same thing. It's the same principle here, it's the same thing. So when you square the deviation from the mean and you add it together, that is sum of square. Now, the problem with sum of square is that the value now will not depend on the sample size. Like now we have 5 families here. The sum of square we're going to have will be different from if it is 10 families are involved, or 7 or 20. So the bigger the family, of course, you expect is bigger the sum of square. The number, that is, the bigger your sample size, the bigger the sum of square. So intelligent people also say, okay, what they did the mean to calculate the mean, because the mean, when you have many values, you want to know, you are looking for one value. I will solve the proof, I will just give you average. So that was how you calculate sigma s over n, that made you to get the average, which is the mean. So the same thing with sum of square. So what you want to see, we have already have square deviation, addition of the square deviation is the sum of square. Then why can't we have the average sum of square? That is, you want to, somebody is making noise, please. Please put yourself. That is Peter. Now, you now sum it together. If you sum it together, you have sum it together, if you want to find the average. In this way, that calculating the average is quite different from calculating the average, the normal average, which is sigma s over n. This one will be the sum of squares, that is the sigma x minus s bar square over the degree of freedom. The degree of freedom. And that takes us to that concept, the degree of freedom. Many people find it difficult to conceptualize. The degree of freedom, before we move further, it's good to unravel some, at least lay some foundation for the degree of freedom. It's good to lay some foundation. What does it actually mean? Now, when you have a group of observation of item that you have, you remember that we talk about variable and data, the value of variable data. And the variable are characteristics that assume different value for different participants, for different subjects. Age, all of us, age is not the same. The only thing that is constant among us is that we are all human beings. That one is not a variable among human beings. Is he human being or not? We are all human beings. That's constant. But we have different age. So age is a variable. Sex is a variable but if everybody here, you have studied, they are men. Sex is no more a variable because it doesn't vary among people. But when you have studied general population, both men and women, sex is a variable also because it's not the same for everybody. So variable, the values of variable can assume the data, collect your data. Now, because when you gather the variable, the value of the variable, that is data, for a number of observations now, maybe about 20 or 30, whichever, at least more than one person or more than one subject. Now, if you have calculated an entity, something like the mean now, it's already fixed the total. You remember when we calculated the mean, we say mean is 5, and the number of families is 5. So the total number of children will be the mean times the number of families, which is 25. It's already fixed. If you look at it now, what we want to calculate now, the mean is already involved. It's assumed that you have calculated the mean, because if you have not calculated the mean, you cannot calculate the deviation from the mean. Sorry, I'm in a lecture, I will call you back. I'm in a lecture, I will call you back. So you cannot calculate the value for the mean, you cannot calculate the mean deviation if you have not calculated the mean. So because of that, it is assumed, because we are talking of having average square deviation from the mean now. So that is how the concept of degree of freedom came here. So something that we calculate which has fixed the total value. So not all of them cannot vary their value again, because we call them, originally we talk about variable that can assume any value. So in this case now, x minus s bar square for each of them all of them cannot vary their value. All of them are not, in that case, you cannot call it purely variable, that all of them will vary their value. It's not possible. Some will vary, some will not vary. So the degree of freedom will not, out of this number, how many can vary the value? That would be the degree of freedom. The simplest way to explain it, maybe in a social context is, assuming you have a meeting for 5 people, 5 of you want to do board meeting, and they have arranged 5 chairs for you. And the first person that arrived will sit on one chair. He has choice to make among 5 chairs. In fact, if he says I sat on one and it's not good, he will change it. So if the first person has choice to make among 5 chairs, the next person to come to sit, we have choice to make among 4, the remaining 4. The next person we have choice to make among the remaining 3. The number 4 we have choice to make among the remaining 2. The last person does not have choice. You are not making choice. This is only one option. There's no choice. You only have a choice to make if you have more than one option. So that person, for the fact, it's not the number of choices now and the number of choices you make now. Is the fact that only 4 out of 5 make choice of where to sit. So the degree of freedom is 4. That is 5 minus 1. 5 minus 1. So somebody asked me sometimes ago, a few weeks ago, he said in a simple term, what do you want? What is the degree of freedom? So the degree of freedom is the number of item minus 1, number of entity minus 1, because every entity can vary if the total value is fixed, has been fixed. So every entity can vary until the last one. The last one, whatever remains is for the last one. So actually it may not be the last, but the issue is that 4 out of 5 can vary, 1 will not be. If they are 100, 99 will vary, can vary, the last one will not be able to vary. If they are 1 million, all of them can vary except the last, except 1. That is the degree of. Another way of looking at it socially, so that you can have a mental picture. If in that your meeting, you were giving for sitting allowance, you were giving 1 million. If they ask you, how will 5 people get share it? It's 200,000 each person, because you assume that all of them are equal. And that one it can lead us to another concept, which is the mean, because you have calculated the average. Because there are 1,000 and there are 5 people, you have calculated the average. Anybody, even if everybody take different amount, but the average will still be, because the total is 1 million, then divided by 5, make it 200,000. So you have calculated because mean is the crudest model. You know, I explained it. I said that expected value is the same thing as mean. That is the value when no hypothesis is true. So now, the person that is the boss, maybe the director, the topmost person there, can decide to take any amount from the money, and the next person will take. If the next person is the next person, manager, after director has taken, manager can take, supervisor can take. At the end of the day, the last person is the most junior, whatever is the main, is the person doesn't have choice to choose to pick. The whatever remains is for that person. So that's another way of looking at it. So if you look at this slide, let's assume we have about 5, the same thing, 5 score, and there are 20 total scores. Sum of the score 20. You will see that each value can vary. This one, instead of 6, can be 7, can be 3, can be anything. But this last one cannot vary its value. If whatever remains, so what you need to do is, if you had all those other ones, remove from 200. They cannot, those ones cannot decide. They cannot vary value, you cannot just allocate any value. You are just allocating value, and the total is 20. You can allocate value for the better. At the end of the day, whatever remains is for the last one. So in that context, the degree of freedom is entity 5 minus 1. So let's go back. We'll still talk about it later, but let's go back here. So we are dividing here now for us to know the average average square deviation now. We divide the sum of square deviation by the degree of freedom. So here now, we now divide it by 1 minus 1, which is the degree of freedom, n minus 1 rather, which is 5 minus 1, 4. Can you see now? Sigma x minus s bar square. Can you see? X minus s bar square. Sigma means addition, sum of square. Divided by n minus 1. That would be, the addition here is 10 divided by 4, which is n minus 1. That is the variance. Variance, can you see now? That is variance. Is the average square deviation from the mean. So some people say mean square deviation from the mean. Can you see? So sometimes if you use the word mean square deviation from the mean, some people they are confused. Mean square deviation from the mean. They make it easy because the average square deviation from the mean. Because the average in the sense that was a mean here before. There was a deviation from the mean. There was square deviation from the mean. When you sum everything, the average of it, which you got by divided by the degree of freedom, that is it, the variance. There's a mean square deviation for the mean. Mean here, or you say average square deviation for the mean. Because by dividing by the degree of freedom, you are calculating the mean also, but it's not the mean of the original variable, but the mean of the square deviation from the mean. So now, because if you look at it, the variance now, it gives you a clue about, okay, this average spread. But that spread they have measured is not the same unit as the original data. If let's say the original data now, let's say is a kilogram, maybe you are looking for the weight of the children set of the baby, the weight of the baby. If it's in kilogram, the variance will be kilogram square because you are square. You have introduced square. So it doesn't make sense. If you measure you use mean as the measure of central tendency, and you now use variance, and the mean as the measure of central tendency carry the same unit as the original data, which is the kilogram. And this one will now say kilogram square. Will you now say that mean is 5 kilogram and the variance is 2.5 kilogram square? So it doesn't carry the same unit as the original variable. So since intelligent people are okay, after all, why we went to square before was because we wanted to avoid this negative that will pin us down to 0. We had it together. That is why we square to remove negativity. Now that we have finished up, why can't we reverse back and calculate and find the square root of the variance? If you now put this variance, the square root will be the standard deviation. So square root is the standard deviation, is this deviation. So why they don't want to call it deviation? See, we have deviation, the real deviation, which is useless along the way if you want to use it directly until you transform it. And so when you now calculate, you reverse back now, they call it standard deviation. But actually is for them not to disobey mathematical rule, because if you decide to even neglect the signs here under the deviation, neglect the signs, add everything together and divide by 5, you will get something close. It's almost the same. You get almost the same thing, but mathematically it's not sound. And that is why you have to move like this and reverse back. So you just need to understand the law. Once you understand this logic, it's very simple. The issue of deviation, square deviation, sum of square, dividing by degree of freedom, and calculate the square root to form a standard deviation. Those steps, they are very, in fact, apart from issue of probability in advanced statistics, those are the things you do in advanced statistics. It's as simple as that. And if you remember Tuesday, I explained the flow chart. Okay, the flow chart was there's a chart I explained. Was it removed? Okay, it's amazing. Didn't save it. I was trying to show the didn't save here. Now I was trying to see for you to see how all this deviation they lead to all those concept correlation. So we want to quickly have a glance, just have a glance of it. So if you have your question, you can start shouting your question. So when we only entertain question when we finish, you can shout your question so that we don't forget. Virtually, look at, I said that there was a place that's okay. All this deviation, all those things, they are the basis for when you see deviation, you see expected value. These are the basis for hypothesis test. So I want to first of all look at the basic. How do you conceptualize the test? All these t-tests, all those. What brought it out? They're about region of chi-square t-test. Is try to understand statistics. We talk about differential statistics. The descriptive statistics you have summarized. You summarize your mean, the standard deviation with mode, median, or with percentage if it's categorical variable. Now you want to know this thing you have summarized is statistic because the value of a sample is from sample. What you are interested in is parameter in the population. So you may want to know, this statistic, is it close to the parameter? Can I confidently say this is what is happening in the population, so that when they quote me in a study, say so at all, they're able to say this study was done. They will refer to the population as a reference population, whereas a few sample from the population you took. Now that is the domain of inferential statistics, and that's where the hypothesis testing comes in. Now, virtually all hypothesis tests are actually the same thing dressed in different names. That is my own observation, my own maxim. There was more Steiner and Strainer and Norman said something. They say nearly all statistical tests are based on a signal to noise ratio, where the signal is the important relationship and noise is a measure of individual variation. You will see that. Let's have a glance. Now, the general formula for a test statistic is, you will see, very funny. Variability, when we talk about variability, is maybe deviation or square deviation or sum of square deviation or variance or standard deviation. You know, those are the steps we just look at now. From the mean, deviation first, square deviation second, sum of the square deviation, which is sum of square, then the variance, which is the average sum of square deviation, average square deviation, then standard deviation, which is square root of variance, 5 of them. So when we talk about variability, any of them can surface as that is variability, how things vary. If somebody score 70%, another person score 50%, you can say, oh, what's the difference? That's the variation between them. The difference is a form of variation also. So that's why when we talk about variability, it's a compound word that you talk about. If you will say measure of variability, or you say even the highest minus the lowest, range is a form of a measure of dispersion. Even deviation, that deviation is a form. It's only that you cannot calculate the average to give you 0. The individual has the deviation. Then the square deviation, the sum of the square deviation, the average square deviation, which is the variance, the square root of the average square deviation, which is the standard deviation. So test statistics is actually the variability between, if you are looking at the two groups, now you want to find difference between two groups. What is the variability between the two groups or between the three groups divided by the variability within the group? It is believed that when you are saying that two groups are different and the difference statistically significant is that is really different, you must be able to prove that if you put the difference you have observed, which is the between group, and the difference that is within, when you now make the difference between group as the numerator and the one within the group are denominator, if actually there is a difference between the two groups, the difference between them, which is the numerator, should be far, far, far bigger than the within group, the inherent difference. And not just, if it's bigger, it will be, when you divide it, will be greater than 1. Not only greater than 1, it should be bigger than 1, that in fact it will reach a critical level and say, oh, no, the difference is much. For you to be able to conceptualize it, for example, if I say the average blood sugar for women is 65, the average milligram per dl, the average for men is 60. You can say, okay, the difference is 5. Women have more sugar, averagely is higher in women than men. But you can all conclude the difference you are looking at is the variability between both of them. But you cannot really say, because if you go and do it again, you may get something different. Because among these women that you say the average is 65, some of them even score lower than some men, even score lower than the average for the men. Some score high, they score so lower. It's just the average at 65. Even the men that you say the average blood sugar is 560, some of them have higher than some women. And some of them even have higher than the average for the women. So that is it. So there are differences within the women and men. So there's a way if you can measure the difference. If the differences within their group, it is only when the differences within their group is not as big as the difference between the two groups. That's where you say the two groups differ. And that is the logic behind putting the difference between groups as the numerator and the difference within group as the denominator, and now see and now use it as a statistic. That statistic, it can be anything. It can be t-test, it can be ANOVA, it can be chi-square, it can be any statistic. That is the logic behind any statistic. So it's the same way. I'm saying the same thing this same way. Variability between groups with the same thing. Observed value minus hypothesized value, which is expected value. Normally what is used to measure the variability within is the standard error. So with all those things, if you go and watch all those lectures, we explain them. Under inferential statistics, we talk about standard error. All those things, we have all the lectures that are there. The essence of this lecture is just to let you know that the advanced statistics, there's nothing advanced, there's nothing, it's not complex. It's just a move when you see something advanced, just you are moving further. And that is why, remember in mathematics in secondary school those days, the mathematics and additional mathematics. Later, there's nothing additional because mathematics are there, it's there. It just the issue there is that at the lowest level, you teach basic things. As you are going higher, you teach advanced things, the same thing. When we were in primary school, then it was arithmetic. But the student now is mathematics, they call everything. Even if the professor in university is professor of mathematics, it's the mathematics that they are doing in kindergarten. The only difference that you start from the most basic on the primary school, then as you are going advanced, higher, moving further. And that was why they called that one further mathematics instead of additional mathematics. So it's the same thing here. So observed value and so standard error is a measure of variability within group. So the difference between the two groups divided by the standard error, if it's big enough, or we say significant. So another way of saying is variance explained by your study over variance not explained. Because those one explained by your study, they are within the group themselves. So if you are able to effect all over error, so that's a different way of conceptualizing it. So for t-test now, look at a formula, you see something like x bar minus mu, one sample t-test. The difference between the mean in your group and the mean in the population. Mu is the mean in the population. That is the variance between them, the difference between them over the variance within which is the standard error, s all over square root of sample size. Because standard error is standard deviation, s all over square root of standard sample size. Can you see? Standard deviation, what we just talked about now. Standard deviation, the standard deviation you calculate divided by the square root of the variance of the sample size is the standard error. So the difference between what you calculated and the difference between and the population value divided by the standard error is the t. So one sample t. That's all. That's the test statistic. Look at the pair sample t. This one is bar d. What they did here is that because there are two groups, and there are two observations from the same group of people. They, of course, we can call it two groups of observations. They from the same group of people. So when you have a score before and after, you minor one from the other, maybe before from the after, or after from before. It doesn't really matter which one. When you minus it, the difference, you now calculate the mean. That's the bar D. D is the difference between the two measurements. Then bar D mean of the difference over the standard deviation of the difference. Well, let's say the standard error of the difference, because the standard error of the difference, standard deviation of the difference over the square root of sample size. Can you see? So the difference now, which is the variability over the standard error, that is the pair sample t-test. If you come to independent sample t-test, two groups. Can you see x1 minus x2? The two groups, you look at the difference over this formula you see here just looks complex. Is the standard error, the one the denominator is the standard error of the difference between the two groups. Because it's two groups now, that's why it look complex. But you can see here is one group. It's just simple. It's the same thing. S square is standard deviation for the two group over the sample size. You now put everything under the square root. So when you look at ANOVA, what ANOVA look is variance or mean square. If you remember, another way of talking of say variance is mean square. We have already said it now, because variance is mean square deviation from the mean. So sometimes they call variance mean square. I call it variance or mean square. So mean square between group, you know, in ANOVA you are dealing with 3 or 4 group, many groups. The mean square between them, mean square within them. That is the F ratio, F statistic for variance. And the mean square between group, this. How do you get it? You look at the mean between group minus the total mean, grand mean, over number of group minus 1, J minus 1. This one, the mean square, or the thing shifted within group, is the mean, the each value minus the mean deviation, divided by the addition of the degree of freedom, number in each category minus 1. So if you look at it, just know that the F ratio is mean variance between group over variance within group. So you look at it, everything is just talking about mean, variance, standard deviation. Now, correlation and regression. No, we talk about covariance. I say covariance is a standardized correlation. Look at it. Look at covariance. X minus S bar, because a covariance between two group variables. So if you designate one, you say one variable is X, the other one is Y. So deviation, some of the deviation from the mean for X and Y, you multiply deviation of the X and multiply by deviation of Y, sum it together over, calculate the degree of freedom also N minus 1. It gives you the covariance. And if you divide this covariance by their standard deviation, it gives you a correlation. Look at it. What do you see there? You are just seeing something like X minus S bar, the deviation. Here, some of the deviation square for X and Y. That's correlation. So what I'm not explaining, because if for each of those statistics now, under correlation, we are giving lecture. Go and watch the video. You see where explain there the logic, how you get correlation from covariance is there. I'm just trying to tell you that it's not something difficult at all. It's something you can get from that table I explained. Table of mean deviation, square deviation, sum of square deviation, average square deviation, which is variance, square root of average square deviation, which is standard deviation. Now, if regression equation, look at regression. When you are predicting Y as your outcome variable from X as your dependent variable. So there are two things there. Two things that will help you to predict it is this intercept, because it is a model. It's the same equation that is the graph. No, you model it with equation or you model it with graph. It's the same thing. This alpha here is the intercept where the graph crosses the y-axis. This beta here is the slope of the graph. That is how slanted the graph is. So this E here is the error. Because when you try to model, you may not be perfect. The different the error you make is that one. So the regression coefficient, this beta is the, look at it, is close to that correlation of this. Look at it. This is the X minus S bar, Y minus Y bar over S minus S bar. So it's actually the covariance of X and Y over the variance of X. Because the slope, the regression coefficient is a change in Y per unit change in X. So that is why what measures change in X is the variance of X. That's why the variance of X is the denominator. What measures change in Y per unit change is the covariance of X and Y. That is, it is change in Y together with X, and that is the covariance of X and Y. If you divide both of them, somewhere the degree N minus 1 will cancel out. That's what gives you this. And you see, It's still just about x minus y squared, whatever. That's so if you have once you calculate beta, you can calculate alpha. Once you calculate beta, you calculate the slope and the beta. Once you calculate beta now, all you need to calculate the average of y and x. You do the alpha, the slope, and once you now get the beta, and then you have already do the model. All you need to do is when somebody can supply you x, you'll be able to calculate what y is. That is the summary of that. Now, I still want you to know why I put this one is that this issue of sum of square, because I said that sum of square, when you get to regression, you meet it there and ANOVA. Look at the way it works. Look at this. Look at the graph you see. You know, I show you the graph now. What you see, the line you see here is the line. I mean, what the line you see is the regression line. The dot you see is the each value where y and x meet. X is the horizontal, y. So if let's say something like age, maybe something like age and weight now. Age of a child and weight. Age here, weight here. So where age, each value for one child, age and their weight meet here, that will be the dot, the scatter plot. So now, those are the data point. This is the regression line. Now, if you want to analyze it now, you want to get all the, you want to get the regression, how you will come about, because the equation I just gave you, but how does it come, how do you come about it? You can show it, you show it in graph. This is the regression line. But this is the mean line. Why? You know, you are predicting y. X is horizontal, y is vertical. This is the regression line. This is the mean of the y. The line that is horizontal. The regression line is vertical, is slanting. So, you know, these different points are the different values. So, the difference between the mean and each value will be the variation between the mean and the, so you know, some are usually less, some are more. The one that are less will be below the mean, the one that are higher. So if you look at, you remove mean from it, the different, the one below that, the difference is negative. The one above the difference is positive. The deviation, this is what you are seeing as y minus y bar. Can you see? Y minus y bar. The sum of, if you sum all of them, the same sum of square we talk about. Why we are using y here? Because y we use it as the, because there are two variables involved here. X is there, y is there. We usually denote any variable that is there at exposure as x, as outcome as y. So here we are saying y. X, y minus y bar, the mean of y. Square it, sum it. That is sum of square. So sum of square, the total sum of SST mean total sum of square is defined by the mean, because the total sum of square you can get in that data is defined by the mean. You see. Then the sum of square, what you did here in the regression is that the regression fit it, it didn't fit it perfectly. The remaining one is the residual, sum of square residual. That is the difference between each point and the regression line. That is y minus y. If you look at it, it's not bar, is the difference, the regression, the error, the mean error, average. You know, this one, okay, there's the error. This one, this y here is the predicted value. What? Okay, look at it for you to order. That's why I put this one here. When you see the line now, each value, the difference between each point is the observed value, what you observe your data. Then where, if you draw a particular line from each point to the line, that point where it means the line is what the line, regression line predict the value, which is this one you see here. So y minus predicted value, that is the error. Can you see? That's the error. So when you sum everything together, sum of square residual error or this one. Then The model, the improvement made by the model is if you overlap these two, you remove this from this, give you. If you remove this from this, it give you this. That is. And when we talk about R square, is sum of square model over sum of square total. So we'll not talk much about that. I just want to create that picture. So because if you go and watch, listen to a lecture, ANOVA or regression, everything you grab with them. Now, the last one we just discussed, we close. It's just, we discussed that degree of freedom. How does it work? If you look at it, in all this ANOVA t-test, the degree of freedom will come into play. Before you can finalize, do t-test, t-test, the chi-square test, ANOVA, regression, the degree of freedom should come. We have already to say that the total number of observation minus number of independent constraints imposed on the observation. I have already explained it. The number of entities minus 1. Number of observation minus there's a constraint. We said that in their constraint, the inability to vary value is the constraint. So 1 cannot vary value out of the entity. So that is why the degree of freedom is the entity minus 1. But when we say, that's why we say entity, we cannot just say, because there are many perspectives to it. That was when somebody said, what's the same? How will you say degree of freedom? I said, the number of entity minus 1. Because it varies, the entity means different things in different contexts. Now, within 2 minutes, we just look at the context, we close the lecture. Now, when you are dealing with categorical variable, because categorical variable, there are manageable number of categories. That's what it means. The outcome, the number of outcome is manageable. Like when you say sex now, there are 2 possible, male or female. If you say ethnicity in Nigeria, you can say Hausa, Igbo, Yoruba, others. Even this, we say we are over 300. But we know how to classify ourselves, manage ourselves like that. Now, if it is a number of words, you can see you have one G1. In the hospital, you can count the number of words. It's categorical variable. The different, no number of words per se, the different type of words. Different type of words. May say, or different department, different department. O&G, pediatrics, internal medicine, all this. Or you see, like SK, maybe there are 5 categories. Or you see, say the tumor classification, the way differentiated, moderately differentiated, they can give you 5 categories, whichever way, manageable number. If they say marital status, married, single, divorced, separated, widow, finish. So that's characteristic of categorical variable. You have limited category. So the degree of freedom for that variable will be number of categories minus 1. Simple. Because the number of categories, the possible outcome, that is number of possible outcome minus 1. If it is quantitative variable, because that one, by nature, they are unlimited number. If they say how many possible blood sugar, so it's infinity. The number of possible blood sugar is infinity. Because it can be 60.1, 60.2, 60.0111. So even between 60 and 61, blood sugar is unlimited, possible value. So for quantitative variable, because of that nature, then it has to do with your sample size. So the degree of freedom will be the sample size minus 1, n minus 1. Can you see? Categorical variable, the degree of freedom will be number of category of that possible outcome of that category minus 1. While for quantitative variable, it has to do with your sample size minus 1. Now, that is just on the lighter note. But most of the time, you don't use the degree of freedom in the simpler form, simple form like that. You use it in calculating a particular statistic. And the way statistics come now will now determine what the degree of freedom is. So when you look at the degree of freedom of chi-square now, if you are calculating chi-square involving contingency table, where you have row and column, because we are looking at association between 2 categorical variables. So because both of them are categorical, so you now give you a contingency where you multiply the 2 number of categories together. In that case, you have row and column. So it's actually the degree of freedom for one category multiplied by the degree of freedom for the other 5 categories. So if maybe you are looking at sex and socioeconomic status, sex is 2 categories, socioeconomic status 3 categories. So in the chi-square now, the degree of freedom will be sex degree of freedom, which is 2 minus 1. Maybe it's along the row. Then socioeconomic status 3 minus 1. So that will be 1 minus 2. So number of row minus 1 and number of column minus 1. So when you are dealing with chi-square with contingency table, that is the degree of freedom. Because 2 variables are involved. So you have to calculate, multiply the degree of freedom for the 2 variables. Now, if you are dealing with a chi-square for goodness of it, in that one, it doesn't involve contingency table. So it's just the category, just the same thing. Number of category minus k minus 1. Number of category. If you are dealing with a NEMA chi-square, that was a little bit complex. We would always go into detail of that one, but just know the degree of freedom k, the number of, you don't know McNema or McNema-Barker is a variable with a certain number of category, but you measure the variable 2 times, before and after. So the k minus 1. So the degree of freedom will be k into k minus 1 over 2. If you go and look at the lecture on that of McNema, it's well explained there. Everything, the logic behind it, how you generate it through combination is there. So the degree of freedom of a t-test, of course, 1 sample t-test. Since it's only 1 sample, n minus 1. Pair sample, n minus 1. Pair sample, why is n minus 1? Because it's the same group of people, it's only you take your observation 2 times. So it's the same group, it's just 1 sample t. But you take your measurement 2 times. That's why it's n minus 1. If it is independent t-test, 2 groups, you are comparing 2 groups now. So n minus 1 plus n minus 1, because there are 2. So it will be n plus n1 plus n2 minus 2. So n1 minus 1, that's for this first group, n2 minus 1 for the second group. It's the same thing as say n1 plus n2 minus 2. So if you are looking at degree of freedom for ANOVA, that one, because there are 2 aspects of it. You know, there is between group and within group variance. So one of the numerator, which is mean square, with the one for the numerator between group, j minus 1, number of group minus 1. If there are 3 groups, 3 minus 1. Then that's for the numerator. The degree of freedom for the denominator will be within group. That is, you know, if maybe for each of the group there are 5, 5, 5, for example, n minus 1, the summation of all of them, it doesn't have to be the same anyway, it's summation of all of them. Summation of the degree of freedom for each of the group within group. That will be the numerator. So the total degree of freedom will be the numerator plus the denominator. Now, degree of freedom from regression. So look at it here. You can see the sum of square we're talking about. The sum of square for total sum of square, the degree of freedom will be n minus 1. That is the total, the sample size minus 1. Then for the regression, you know, sum of square regression or residual, it will be k, which is the number of the group now. Now, no, not the, that one is not regression, sorry. The regression line, which is number of groups, that's between number of the group, number of, what I call it now, to make it easy, is the number of variables, rather, independent variables, rather. Then the number of coefficients for the regression now, for the residual, this is the residual, n minus k minus 1. That is the sample size minus number of the variables minus 1. They give you. That one will be plenty. So just for you to get the concept, because you see that at each level, different analysis, you see that apart from the fact that everything is all about deviation, variance, you know, deviation, variance, standard deviation, then the degree of freedom comes in. At the end of the day, the probability you use to interpret it. That's why we talk much, we talk, see depth into some probability distribution next week, so that at least the area of probability in statistics be able to have a clue. I think we'll stop here. Any comment, any question? I didn't see any chat, so it means that it's well understood, if I'm not mistaken. So any question? Any question? Okay, nobody talk. Okay. No question?
Thank you, sir.
Okay, go on. Well done. You have question? No question, okay? Is that when you don't have question like that, everything is confusing or everything is understandable?
Standard deviation. Just I know that it's not really, but because I wanted to just find out the difference between standard deviation and standard error.
Ah, it was staring at you there. We talk about it. Standard deviation. With standard error is standard deviation over square root of sample size. Please go and watch our video on introduction to inferential statistics. It's well spelled out there.
Okay.
The logic behind it, why the usefulness of standard error. So I also talk about, I said that will measure the inherent variability. If standard error is very small, it means that your estimate, is close to the parameter. And it may also mean that that variable in the population, their value are not far, they are close. If the standard error is light, it may mean that you estimate what you calculate in your sample is far from what is in the population. Or another thing is that that attribute is usually far apart in the population. That's because standard error is standard deviation of sampling distribution. Yes, I'm a standard deviation of sampling. I don't want to go into that sampling distribution now because that's not where what
yes, sir.
But if you go to that inferential statistics, you see under sampling distribution, talk about standard error, which is standard deviation of sampling distribution. Some people call it because it is believed that it should be equal to the standard deviation in the population. That's why some people now say standard error is population standard deviation. It's not true. It just believes that it should be equal to it. So it's just oversimplification for somebody to say standard error is standard deviation of the population. No, it's the standard deviation of sampling distribution. But okay, somebody's okay.
Thank you,
somebody
sir.
say okay, that's fine. That's fine. Okay, somebody say well understood. Okay, thank you. Please, what is the difference between signal and is that quotation you? I don't want to, okay. Yeah, it's from okay. Thank you for raising it. But when I say, if you look at it, I say, when we say that all the tests, they are the same thing. The numerator is usually the variability between the group. That is the signal. Then the variability within the group, which is the denominator, is the noise. I don't know if you understand me now. What we are looking for the difference. The difference is the numerator, difference between the two groups. But you don't want to say that noise is not much than the difference, because if you are tuning your radio in those days that we watch, you remember when there was no, or in rural area, when there was no television, when people watch, you don't watch the football, but you listen to football in the rural area. So when you are tuning your radio, if the noise is much more than the signal, in fact, it's only when they say go, everything they are saying that you will not hear anything. So the noise is too much. But if the tone is very good, the noise will be minimized and the signal will be higher. So the numerator is the difference you are looking for is the signal. The noise is the inherent, the denominator, the variability within. Because if the variability will be too much, it will offset. If it's too much and it's offset, it's even much more competing with the different. You cannot say there's any difference. Just like if the noise is too much in the lecture, you will not get anything from the lecture. So the same concept is what we use in diagnostic test. You know, when we plot receivers operating characteristic curve, ROC. So in the last workshop, you didn't attend the last workshop. It's usually the last, second to the last, when we talk about validity, reliability, and diagnostic test. We did that. We talk about this noise applicability. Though you can still go and watch it because we still give the lecture also. Apart from the workshop, the lecture is there. Yeah, you can the person that is even asking the question is subscribed, is a subscriber. So it's like your subscription has expired. So he's a subscriber because you go and watch.
Yes, I will renew it. I will renew it. I will renew it.
I don't talk. Don't talk. I like to when you send text to me. That's why. Okay, you even sent your own text, not privately. Because when people send text privately, I answer the question without making mention of that person. So maybe some people like it like that. So no problem. I think it's well understood now. But if you go and watch that diagnostic test, you understand it very well. The noise and the signal. Yes. Any other comment or any other question? Any other question? No more question. No more question.
Thank you, Ogadro.
Okay, welcome. Okay.
Thank you, sir. Good night, sir.
Okay, good night, sir.
Thank you, sir. Good night.
Okay,
Thank
good
you,
night.
sir. God bless.
Yeah. Okay, I think I'm not even.
Thank you, sir.
You're welcome.